Good afternoon, everyone. Today we're going to sketch this rational function, and then we're going to solve the inequality for when it's less than or equal to 0. Okay. So first things first, let's acknowledge that the degree of the numerator is 3, whereas the degree of the denominator is only 2. That means we're under the case where the degree of the numerator is 1 higher than the denominator, and so that means we're going to get an oblique asymptote, right? So we're going to get an oblique asymptote for sure. Let's write it like that. Now, before we do that, let's see if we can simplify down our expression by factoring and simplifying down. So, if you notice, the cubic function in the numerator can be factored by grouping. If we factor the first two terms, we can get x squared and then times x minus 2. And then if we factor the last two terms, kind of like we do with decomposition with quadratic functions, this cubic function is perfectly laid out to be factored by grouping. And so from the last two terms, we factor a -1, and then we get exactly the same expression inside both brackets. That's what tells us we can factor this by grouping, which is so much easier than using the rational root theorem and going down one factor at a time. Okay. Now, the denominator is easier to work with. That's the difference of squares. And you guys know that factors as x minus 2 times x plus 2. Now, let's finish off factoring our numerator. So the stuff outside the brackets is x squared minus 1, and then the stuff inside the brackets, x minus 2, all over x minus 2 times x plus 2. And now we can do two steps in one. You can notice that the x minus 2 factor cancels out, and so we can simplify down our expression, and in the same breath, we can finish factoring that difference of squares, x squared minus 1, factors into x minus 1 times x plus 1, and now all we have in the denominator is x plus 2, and so this is our simplified expression for f of x, but we have to acknowledge that we factored out the x minus 2 and then canceled it from the numerator and denominator, and that gives us a point of discontinuity at that at the value of x that would make that factor be 0. And so that means when x is positive 2. Okay, that's going to make an open hole, an open circle in our sketch. Okay, exactly where x is 2. So now we've made f of x look a little bit easier to work with, right? What we're going to have here is this numerator is now a quadratic function, and we have a linear factor in the denominator, so it's still a quadratic over linear, which means the degree of the numerator is 1 higher than the degree of the denominator, right? Of course, just as it was originally. And so we're still going to have an oblique asymptote, but now the division process is going to be a bit easier to work with. So let's use long division. Let's divide. If we multiply this out, you know it's just x squared minus 1. And so we're going to divide x squared minus 1 by the factor x plus 2, right? And now we can run through that algorithm. X times what makes x squared? That's x. X times x plus 2 is x squared plus 4x, and we subtract. And so we get negative 4x minus 1. And now x times what makes negative 4x? That's minus 4. Negative 4 times that, negative 4 minus 8. And so we get a remainder of 9, right? That's a remainder. All that matters is that it's not equal to 0, and there's just no variable in that remainder. It's not x plus 9, for example. And so since there's no variable in that remainder, that tells us that f of x will not cross our oblique asymptote. Okay, that's the telltale sign. When we go through the division process getting our oblique asymptote, we get the equation of that oblique asymptote, that quotient up here, x minus 4, serves as the equation of our oblique asymptote, and then the remainder, if it did have a variable in it, we could set it equal to 0, and then that would give us the point of intersection where we cross the oblique asymptote. But since the remainder is just a constant term is never going to be 0 if it's not already 0, and so we do not cross that oblique asymptote. So we can actually start by sketching that. X minus 4, that's a line with a slope of 1, right? That's 1x minus 4. And so we have a y-intercept at negative 4, and then a slope of 1. And so it looks something like this. I'll try to make my sketch somewhat accurate. Okay. So we have our oblique asymptote popped onto our graph. Now we can look at the denominator of our function. That provides us with our vertical asymptote at x is equal to -2. So that'll be a nice vertical asymptote at x is equal to -2. Not sure what that noise was. And now we won't have any horizontal asymptote, right? That horizontal is replaced by an oblique asymptote. Now we can look in the numerator to get our two x-intercepts, right? And so if we do that, these two factors give us our x-intercepts, right? And those are going to be at 1 and -1 respectively. So 1, 0 and -1, 0 respectively, which means here and here, right? And now we can also get the y-intercept pretty quickly without too much work. Identifying a y-intercept just means plugging in an x value of 0 and plugging in an x value of 0 means every term with a 0 goes to 0. And so all we're left with is 2 over -4. That's -0.5. And so that means that we have a y-intercept at -0.5 roughly here. And that looks like our turning point in this upper region of our sketch, right? Now we have 3 points graphed in. We should look for some points in this left part of the sketch. So we have our vertical asymptote at x is -2. Let's plug in some x value that's to the left of -2. Let's use -3 to keep things as straightforward as possible. So plugging in -3 we could plug it into the original. We could also plug it into our simplified version. This is much easier. And so that means f of -3 is going to be, that's -3 minus 1 over -3 plus 1 all over -3 plus 2. I actually think it's going to work out to be a very nice value. So that's going to be -4 times -2 all over -1, which is 8 over -1, which is -8. Right? And so that means when x is -3, y is -8, meaning we get a point somewhere around here. Okay? And now that we have a few points on our sketch, you've maybe done enough of these that you can start to kind of see what the curve is going to look like in its entirety. So in this top right triangular region, we're going to go, remember, our function is going to hover right along the asymptotes, right? So this oblique asymptote is the behavior of the function as x heads towards infinity. And so we're going to go right along that oblique asymptote, like so. And then, of course, right along that vertical asymptote, kind of like a Nike swoosh, right? And then kind of the symmetrical shape down in this bottom left region. This we can serve as our kind of turning point. And again, we're going along the asymptotes. And so along that vertical asymptote and along that oblique asymptote. And that is, roughly speaking at least, the sketch of our function f of x. Now, if we want to solve the inequality when is f of x less than or equal to 0, we need only to look at our sketch, right? And we want to write our solution in interval form. And so f of x is less than or equal to 0, that is to say graphically on or below the x-axis, everywhere down here, right? That means anywhere when x is less than -2. So we can write that. Let's write that in here. When x is less than -2. It can't actually be -2 because the function is undefined at -2, right? That's what a vertical asymptote means. And then we also have another option. X can be in this tiny region here, right? It's less than or equal to. So that means anywhere between the x-intercepts, including the x-intercepts themselves. And so our two x-intercepts were at, where were they? At 1 and -1. And so that means if x is anywhere sandwiched between those two values. That is in set notation. If you rather interval notation, we can say when x is anywhere in the interval from negative infinity to negative 2, we should actually be mindful of something. I lost sight of our point of discontinuity at x is equal to 2. And that is definitely something that's important to factor in. So let's finish this off. Where was the y-intercept? The y-intercept was at negative 0.5. This is a lot. Please have grace. The point of discontinuity is at x equal to 2, and now we can't plug x equal to 2 into the original function, right? Because since x minus 2 canceled out of both the numerator and denominator, if we were to plug in the value of 2 in for x in the original, we would get 0 over 0. That's why the x minus 2 factor canceled out, right? And so we can't plug it back into the original. We have to plug it back into this simplified version of f of x. And so let's find where that P.O.D. actually lies. F of 2 is going to be, let's plug into this simplified expression. And so we're going to have 2 minus 1 times 2 plus 1 over 2 plus 2, right? And that means 2 minus 1, that's 1 times 3 all over 4, which is 0.75. Does that look right when x is 2? Y is 0.75, so P.O.D. at f of 2, which means we have a point at 2, 0.75. That's our point of discontinuity, right? And so that means that right here we get an open point on our sketch, okay? That function is undefined at this point of discontinuity. So we get an open point right in that spot. And so that means that we have to take that into consideration when we're writing our solution to the inequality, right? The function is undefined at that point of discontinuity, and so it can't be part of our solution. But it turns out since f of x is bigger than 0 at that point, it was never going to be part of our solution, but it certainly is something to keep in mind because sometimes it will be. And so now to finish off solving the inequality in integral notation, we can go from negative infinity all the way to the left up until negative 2, not including negative 2, so round brackets. Union, we can also go anywhere from negative 1 to positive 1, including those endpoints, because it's or equal to. And so union, square bracket, negative 1 to positive 1, square brackets. And we're done. So, lots to keep in mind here. Oblique asymptote, degree is 1 higher on top than on the bottom. Factor it, look for any points of discontinuity, any factors that cancel out, get the simplified version, sketch the simplified version, draw your asymptotes, your x-intercepts, y-intercept, any points that might be useful to sketch your curve, and then solve the inequality once you have your sketch nicely laid out on your axes. I hope this helps, and thanks for watching.